Today we will talk about synthetic polymers. So, this will again be a reasonably brief talk. So, I will only focus on things which have been studied extensively. So, obviously you can look at any synthetic polymer as long as it is biocompatible. However, we will focus on some things where people have actually demonstrated reasonable success with respect to using it for tissue engineering applications. Okay. So, why do you want to use synthetic polymers? Yeah, as long as natural polymers do the work, we would not have to look at synthetic polymers, right. But we already discussed natural polymers have some serious limitations, right. Source could be a problem because it can actually cause immunogenicity and contamination issues are there, batch to batch variations are there, your properties are not really tailorable. There are some problems which has made people look at synthetic polymers. So, the advantage is they are more uniform and they have predictable chemical and mechanical properties. However, problem with this would be it is a foreign material, right. It could have some problems, but you can actually design it for specific purposes. You can actually make it free from toxins and contaminants, because you are going to be synthesizing it in a lab. You will have a lot of control over the quality of the material you are producing. So, you have choice over the monomers, the initiators, the reaction conditions and any additives you want to add to the polymer and so on. So, this way you can actually tailor many of the properties like crystallinity, melting and glass transition temperatures, molecular weights and side groups. So, these will give you desired properties which will actually be suitable for appropriate applications. Yeah.
Between bioimplants and scaffold.
Okay, so if I am going to say an implant is generally not biologically active, in the sense that it is just there to provide some kind of a replacement. Okay, it is not helping in regeneration of the natural tissue. A hip and joint replacement is an implant, right. So, you basically use a titanium alloy and you put it in the body. That is not going to help in your bone growing back. Whereas a scaffold, a tissue engineered scaffold is supposed to help the bone to grow back. So, that is why if you were to use a hydroxyapatite ceramic, that would help in bone ingrowth. It will help in the cells for attaching and formation of new matrix, and it will integrate itself with the bone, with the existing bone. So, that would be a scaffold from a tissue engineering perspective.
So, most of the times it will be inert.
Implant will usually be inert, yes.
But there are some degradable bioimplants which can be helpful for the bone growth, right?
So, you have degradable implants, yes. So, degradable sutures, all those things are there. So, because it is not permanent does not make it bioactive. I am talking about activity. So, if you are going to load, so if you are going to use something where you are delivering molecules, then it automatically becomes active. That would make it more related to a delivery mechanism. So, it is a signal based approach, so which we are talking about, right. So, here we are looking at the material itself which can help in cell adhesion and so on. Okay. So, does that answer your question? Okay. So, what was the material you are talking about when you are saying material degrades?
Magnesium degradable implants are there.
Okay.
Of course, the reaction it will be made to the the prolonged, the immediate degradation it will lead to that bone growth.
Yeah. So, I haven't actually read a lot about magnesium and its bioactivity. I know Professor Sampath Kumar does that, so I don't know exactly the biology behind it. But if magnesium by degradation can actually stimulate it, then it would actually be a bioactive material. So, like a hydroxyapatite, right. So, it just depends on the biology behind it. I am not very confident about the biology of magnesium.
Because nowadays all the implants are coming with hydroxyapatite coating only, so that the reaction will be more like active, bioactive in nature.
So, that is for host integration. So, to make sure that if you have a hydroxyapatite, some ceramic coating, it makes sure that the cells can attach and your chances of dislocation and loosening actually come down, because it now integrates with the bone, right. So, that is the idea. So, host integration is another aspect of implantation. So, that is another major concern when it comes to even tissue engineered products, right. How you integrate it with your body is going to be a question. Okay. So, with synthetic polymers you have certain advantages. So, people have tried different synthetic polymers, and they always stuck to things which have already been proven to be biocompatible. Most of the there are a lot of biocompatible synthetic polymers that are known. Many of them have even been approved by FDA for specific applications. It might not be specifically for tissue engineering, but you would usually have it approved for various applications. And if it has shown to be, if it is shown to be compatible, then you would want to try to see whether it is actually effective as a tissue engineering scaffold. So, broadly these materials are classified as biodegradable and non-degradable. Biodegradable are the ones which basically degrade in your body in vivo. Non-biodegradable do not degrade inside your body. So, examples for the biodegradable would be PLA, PGA, PCl and so on. These usually degrade based on hydrolysis. It is a simple hydrolysis reaction which will just degrade these into products that can be excreted out. Whereas non-biodegradable do not usually, it cannot be hydrolyzed, there are no enzymes which can actually break it down. So, because of this they have to be confined for specific types of implant, like if it is going to be a permanent implant, then you might want to use a non-biodegradable material, or you would try to chemically modify these non-biodegradable materials to make it biodegradable. And you can also use it in blocks of low molecular weight, so that there can actually be elimination from the body. So, for example, polyethylene glycol is not biodegradable, but below a certain molecular weight it can actually be excreted through your kidney. So, if you use it in that molecular weight, then it will not be a problem, it can actually be removed from your body. So, PVA, polyacrylic acid, polyhema are all some of the examples of non-biodegradable materials which have been tried out for tissue engineering applications. So, we will go through some of these in reasonable detail. So, this is PGA, polyglycolic acid. So, this is a linear polymer of glycolic acid. So, glycolic acid is actually produced in your body during normal metabolism, which means the degradation products of polyglycolic acid are not going to have any toxic effect in your body. However, this material itself goes through bulk degradation. It is not just surface degradation, surface etching is not what happens, it just bulk degradation happens, which means it can actually get degraded reasonably quickly. So, in vivo degradation happens only through hydrolysis. This process can also be catalyzed further by molecules which have esterase activities. So, the enzymes that are that have esterase activity can rapidly hydrolyze PGA. So, the in vivo degradation studies have shown that it usually loses its strength within the first 2 months, 1 to 2 months it loses its mechanical strength, and complete degradation happens within 6 months. So, this has been approved for FDA, it is approved by FDA for biodegradable sutures. So, you would have come across these in surgeries, people now use biodegradable sutures rather than the regular sutures, so that you do not have to go back again for removing the suture, right. So, these will actually be absorbed by your body. So, this is one of the most commonly used polymers which are bioabsorbable. So, it has been extensively studied. There are commercial products out there which use PGA. So, yeah.
There is only glycolic acid produced in the body, or even PGAs?
No, glycolic acid is produced in your body, not PGA. Polyglycolic acid is not produced. You can actually prepare polyglycolic acid which just gets hydrolyzed to glycolic acid. Tissue engineering studies of PGA have actually been done. People have shown that different types of cells can actually adhere and grow on top of these cells, on these polymers. Another set of polymers which have been studied extensively is PLA, or polylactic acid. So, here these are actually made from 2 different monomers. So, one is, it is possible to use lactic acid and prepare the polymer. Other option is to use the cyclic diester, which is lactide, and then prepare this. So, the direct condensation of lactic acid monomers to form PLA should be done at temperatures which are milder. So, only then you would prevent the formation of cyclic diesters. So, if cyclic diesters form, then you go for through the ring opening polymerization of the lactide, so which can be catalyzed by different metal catalysts. So using this you actually prepare PLA, and lactic acid itself actually exists in two optically active forms, which are D and L. So lactide, which is a cyclic diester, can exist in three isomers. It could be L-lactide, D-lactide or DL-lactide. And the polymerization can form semi-crystalline polymer or an amorphous powder depending on what is used for which stereoisomer is used for preparation of PLA. So if PLLA is formed, then it is semi-crystalline. DLPLA, which is the both D and L together, that forms an amorphous powder. So the advantage is you can actually tailor the strength and the degradation rate based on this. So PLLA is slow degrading with very high tensile properties. Because of this, it has actually been studied for many bone applications. Commercially, it has been approved for orthopedic fixation devices. So like bone screws and things like that. So they have actually used PLA for doing this. And the D and L combination has lower strength and a faster degradation rate. So we can try to combine these to get desired properties. So PLA is also used, is one of the most commonly used inks in 3D printing. Most of these 3D printers would use PLA. So PLGA is basically a copolymer of these two. So this is to try and use both the advantages. Okay. So ring opening copolymerization of the cyclic dimers of glycolic acid and lactic acid is done to get this PLGA. So what people have shown is there are different forms of PLGA can be formed based on the initial concentrations, initial molar ratios of lactic acid to glycolic acid, and they are usually written as PLGA X is to Y, where X is the concentration percentage of lactic acid and Y is the percentage of glycolic acid. 75-25 means 75% lactic acid, 25% glycolic acid. So the advantage of doing this is the physical properties themselves can be tailored. So this also degrades by hydrolysis in the presence of water. The rate of degradation actually can be related to the monomer ratio. If you have very high glycolic acid, then the rate of degradation is faster, because glycolic acid PGA we saw that had a faster degradation compared to PLA, right. So it would have faster degradation. However, this correlation is actually not linear. So in some points it does not actually fit that. One example is 50-50 PLGA. PLGA 50-50 actually shows much faster degradation, which is actually faster than both PGA and PLA. So I do not know the chemistry behind it, but in general this has been observed. So PLGA has been approved for many drug delivery applications and has also been extensively studied for tissue engineering applications. People have shown many advantages to using this. There are some disadvantages as well because of the acidic nature of this material. The pH in the localized regions could actually become lower, which could cause cell death, and it could cause some damage. So people have in some studies have shown that. So trying to use this has its own advantages and disadvantages. Polycaprolactone is an aliphatic polyester with semi-crystalline properties. So the repeating units are 1 ester group and 5 methylene groups. So the structure you can see there, it is a highly water soluble polymer, and this is formed by ring opening polymerization to form degradable ester linkages. So the degradation occurs by surface or bulk hydrolysis of these ester linkages. So degradation is actually very slow, and it can actually be present in your body for up to 2 years. So it is usually used for processes where the regeneration is going to be very slow. So PCL has actually been used in bone tissue engineering applications. So they have shown that osteoblasts can actually adhere to this PCL and produce ALP. ALP is alkaline phosphatase, which is a marker for biomineralization. So when ALP production is increased, then you know that there is mineralization of bone. So people have shown that when osteoblasts are cultured with PCL, it shows an increased ALP production. So to optimize the rate of degradation, many studies have tried to use PCl copolymerized with other materials like PEG and PVA and so on. So, the ones which we looked at till now, PGA, PLA, PLGA and PCl are all biodegradable. So, the ones which we are looking from here on out are non-degradable, non-biodegradable. PEG is a non-biodegradable material, however, it is very highly hydrophilic, it has very good swelling ability. So, because of this reason, it is actually used extensively in formation of hydrogels. We will look at what hydrogels are and we will go into details of hydrogels later, but can you tell me what you understand with the term hydrogels? Have you come across the term hydrogels?
As a simple definition, it's a matrix which holds
Okay.
water.
So, it can absorb water, right? Okay. So, that would be one, sorry?
Highly hydrophilic.
Okay, highly hydrophilic. So, if you were to take a sponge, right, and you dip it in water, that also holds a lot of water, right? So, does that make it a hydrogen?
It should interact with water.
It should hold water. So, it is not just that it absorbs water, it should also hold water. A sponge, if you squeeze, the water is going to come out, whereas a hydrogel, if you squeeze, the water will not come out. So, PEG is used because it can actually form hydrogels which are very hydrophilic and it can actually absorb a lot of water. The advantage of that is it will have very limited diffusion problems, right? If it can swell very nicely, if the network can swell very nicely, nutrient transport is going to be very effective. But the other side of it is the linear chain actually leads to rapid diffusion of the material outside of it, which means it just dissolves away and it has very low mechanical stability. So, for this reason people try to create PEG networks by attaching functional groups to PEG and try to cross-link it using covalent or other types of cross-linking. So, this is non-biodegradable but can be degraded by copolymerization, can be made to be degradable by copolymerization with other degradable polymers. And as I already mentioned, below a molecular weight threshold, it can actually be excreted by your kidneys. So, if you were to use it at that molecular weight, then it's usually not a problem.
So, would activated charcoal be a hydrogen?
No. Why do you think it would be a hydrogen?
It's a solid absorber.
It doesn't absorb water, right? It just absorbs other things. It's okay. So, polyvinyl alcohol is another commonly used material. So, this is a water soluble polymer with excellent biocompatibility. Lot of studies have worked with PVA and shown that it is very useful for biomedical applications. And vinyl alcohol itself is not very stable, so it is synthesized using a two-step process. So, it is not just a direct polymerization of vinyl alcohol which is done. So, what people do is they do the first step is the free radical polymerization of vinyl acetate, and the second step is hydrolysis of the polyvinyl acetate to form PVA, polyvinyl alcohol. So, this hydrolysis actually can be controlled. So, you can have varying degrees of hydrolysis. So, just like how you have varying degrees of deacetylation for chitosan, you can have varying degrees of hydrolysis for PVA, and based on the degree of hydrolysis, the mechanical and the physical properties can actually be different. So, it has been used in many applications. PVA, there are actually review articles which talk about PVA for tissue engineering applications. You can go and read it up. It is done for many different things. Only limitation with PVA is it is so hydrophilic that it does not support cell adhesion very effectively. So, in some cases you actually need to maintain a balance when it comes to hydrophilicity and hydrophobicity. If it is going to be very highly hydrophilic, it does not support the cells as much as it should. So, because of this reason people usually use it along with other natural polymers. So, various types of natural polymers have been used along with PVA, cellulose and cellulose derivatives, hyaluronic acid, collagen, all these have been blended with PVA to improve its cell adhesion properties. So, this is just a bunch of other synthetic polymers which have actually been studied. So, you have polypropylene fumarate, polyorthoester, polyanhydrides, polyphosphazine, polycarbonate and polyurethanes, which have all been studied for different applications. Polyurethane, so these are all approved for biomedical use and they have been shown to be biocompatible. So, people have just tried it for tissue engineering applications. You will be able to find papers which talk about other synthetic polymers as well, but these are some of the more commonly used synthetic polymers. So, another class of polymers, synthetic polymers would be the conducting polymers. So, polymers in general do not conduct electricity, right. So, they are very poor conductors of electricity. So, there are a special class of polymers which are called conducting polymers. So, this is actually a Nobel Prize winning discovery. They won this discovery actually won the Nobel Prize in 2000, I think, for chemistry. So, the conducting polymers which are shown here are polyaniline, polypyrrole and P dot, which is polyethylene dioxythiophene. So, these are some of the common conducting polymers. So, these as polymers themselves have conducting properties. However, they have some limitations because they do not have the desired mechanical properties. They actually are brittle when they are fabricated into scaffolds and other materials. So, they are blended with other polymers to prepare conducting polymer composites. So, these are they have actually been fabricated into multiple things and have been used for different tissue engineering applications where electrical properties of the scaffold play a role. So, people do try to prepare these materials in different ways, and we will actually look at how to fabricate these scaffolds. So, fabricating a scaffold is actually a crucial aspect, right. So, having a polymer is one thing, from the polymer to actually make it to resemble the ECM is a serious thing which we need to look at. So, the fabrication strategies have to be optimized. There are many different strategies. So, these are just a bunch of them which I have shown here, and you can look at many other things as well. So, leaching methods where you have solvent casting and salt leaching, ice particle leaching, gas foaming and salt leaching, these are all some of the leaching methods. And you have microsphere formation where you can have biodegradable microspheres or macroporous beads or particle aggregated scaffolds being formed, and phase separation methods like freeze drying or thermally induced phase separation could also be tried, and fiber spinning methodologies to form nanofibers, microfibers, non-woven fibers and so on. Injectable gels can also be prepared. 3D printing is one of the latest technology where people are trying to print many of these things. Okay, so, these are some of the scaffold fabrication strategies. We will discuss some of them here, and 3D printing I will discuss in greater length in the next lecture. So, this is solvent casting and salt leaching. So, this is a very simple technique. So, all you do is you take three things: you take the solvent, polymer and a salt. So, the salt here is NaCl. So, you could also use sugar or whatever, right. So, it is something which can form a crystal. So, you basically mix all of these, and now what happens is the salt has actually dissolved along with the polymer, and you pour it in the mold, whatever the mold could be. So, here they have just shown a disc like mold. You pour it in this mold, and once it is dried out, so you keep it in room temperature or in vacuum to evaporate the solvent. So, you know what you have is a polymer disc in which the salt is dispersed all over, right. So, you put it in water and wash it. So, what will happen is you would have dissolved all the salt away. So, now the positions in which the salt was present have these pores. So, that is a salt leaching technique, and then you can freeze dry it to eliminate all the remaining solvents and so on. So, this is a SEM image of a solvent cast salt leached material. So, you can see nice cube kind of pores. So, this is where the salt crystals were present, right. So, those got washed away and you actually got these pores. So, but here what do you think would be the advantage of this technique? Any porous material will give you more surface area. So, this specifically has some advantage.
Semi-permeable properties.
These are all interconnected pores.
Okay, that's actually not correct. We'll get to it in the next thing. But
easy fabrication process because
okay, so it's a very easy process. That's one thing. What
no
else?
heating involved.
Okay. Okay, so milder conditions for processing, all that is fine.
The regular matrix of pores quite easily because the salt will be dispersed everywhere.
Okay, so you are able to get regular pores. So, okay, I will rephrase it slightly to fit what I want to say. So, you can actually control the porosity. So, based on the salt concentration and the type of salt you use, the pore size and pore distribution can actually be controlled. Okay, so that's the advantage here. So, as far as your claim of it being interconnected pores, it's actually not true. So, if you were to look at these points, so these are actually deep pores, right? So, the ones where you see the dark black or deep pores, whereas if you look at these spots which are more grayish or even whitish, they are actually not deep. So, those are, you are saying the polymer surface itself, right? But these are actually pores which have been formed. So, those are places where the salt was present and it has just been dissolved away. So, in some cases you would have gotten interconnected pores, but in many cases you would actually not have very good interconnectivity in this method. Okay, so to get better interconnectivity, that's why you do gas forming and salt leaching. So, what you do here is a polymer gel is prepared, and instead of just adding salt, you add a salt which can actually release gas. So, an example would be ammonium bicarbonate. So, you add this and then you actually evaporate the solvent and put it in water or put it in a buffer. What will happen is you will have the carbon dioxide getting released from this, right? So, this gas is going to get released from the scaffold which you have prepared. So, when the gas comes out, it's going to create these pores. So, that you will end up with porous scaffold. This after drying and freeze drying, you can get a macroporous scaffold. So, the scaffold will look like this. So, if you look at this, even the smaller of the pores would actually have some of these connections where you would actually see that it is reasonably interconnected. So, you would have very small, those are the places where the gas would have escaped out and created these pores. So, because of this, this shows a very good interconnectivity. So, that's the advantage of using gas forming technique. Okay, so, but these are all very simple techniques which people have been using, where they have shown that you can create porous structures. But what would be the disadvantage of this compared to the salt leaching? Density would be way less for any porous material. If you increase porosity, your mechanical strength is going to come down. Okay, as long as you keep increasing your porosity, the mechanical strength will have to come down, right? Because you have pockets of just air. Can you elaborate? What do you mean accumulation? It's non-uniform. So, whenever I ask what is the disadvantage of this compared to something else, it would usually be the advantage of the other technique, right? So, the other technique you had control over the pore size and porosity. Here you have reasonable control over the porosity, but not really the pore size and so on. Okay, the distribution, pore size, all those things you are not. It's not very well organized. So, microspheres, you guys would have prepared it for different applications, primarily for entrapment of enzymes and things. So, the same thing can actually be used in tissue engineering applications as well, but people don't generally use just a microsphere. Although people have earlier studied it, nowadays people just don't use a microsphere by itself because that does not resemble what your ECM is. So, people will use microspheres along with other materials, so where you can use the microsphere to load molecules and so on. So, microsphere shown here is quite simple. All you do is dropping it while the cross-linking media is spinning and you create a microsphere. So, this is a simple PLGA microsphere, I believe, on which human disc cells are actually cultured. So, this shows that cells can actually adhere and depends on the material you have chosen, and you will get nice beads of uniform size. All that you need to control is the viscosity of the material, the rate at which you actually release the material into the media, and also the diameter of the pore which is used for releasing the media. Freeze drying is another commonly used technique. This is actually one of the more popular techniques which is currently being used extensively, even more than salt leaching or gas forming, because it's really simple. All you do is dissolve it, mold it, freeze it and dry it. That's it. As simple as that. So you actually create pores because of this freeze drying technique. Right? So we in the last class or some class I actually discussed freeze drying, right? So freeze drying is a lyophilization technique where you actually have a sublimation process happening. So can somebody actually draw the phase diagram for water and explain the sublimation process? How would it look? Pressure versus temperature. Something like this, right? So which region is which?
High pressure, low temperature is solid. Yeah.
High pressure, low temperature is
Solid.
solid. Okay.
Then high temperature, low pressure is gas.
What?
Steam.
Which is one?
Gas. That.
This one. Yes?
Yeah.
Steam.
And one
Okay.
between both.
Okay. This is liquid. Okay. Confident?
Yeah.
Okay. Okay. So you guys are doing thermo now, right? So now that you have the phase diagram, can you actually tell me what's the process of lyophilization from here?
Basically, at a low temperature, they reduce the pressure, so all the water sublimates. So directly it goes from solid to vapor.
Yeah.
There's no liquid.
You just have to go here. So instead of, usually solid goes to liquid and then to vapor. So instead you just, so it depends on which pressure region you are in, right? So if you are in a very low pressure, so that's why you create vacuum during lyophilization, and at vacuum you make sure that you can actually sublimate it at low temperatures rather than heat it and where you have to have a vaporization process. So the advantage is it creates pores as well as it does not damage the material. It's a very it's done at low temperatures, right? Very low temperatures. So because of this, it does not damage the material. So this was a scaffold which we developed in our lab. This was prepared by lyophilization technique. So you can see very nice pores which are there and like very nicely interconnected, and it resembles what an ECM would look like, right? So this is a.
What kind of microscope is used to?
It's a scanning electron microscope. So we will discuss characterization extensively. So there will actually be there's a lot of things which you can use. So this is a scanning electron microscope. There are different microscopes which can be used for such things. So you get these images. So even the image which I showed, most of these images are actually SEM images only. This is also a scanning electron microscope, and this is also a scanning electron microscope image. So for observing surface morphology, SEM is the most common method used. So another technique which is commonly studied is electrospinning. So in this technique, what you do is you take a syringe and you fill it with a polymer solution, and the syringe dispenses the polymer solution, which is exposed to a high voltage environment. So, and this basically breaks the polymer flow into thin fibers, which is collected by a collector which is grounded, and the collector can actually be a rotary drum, it can be a flat surface and so on. So depending on the collector surface, you can actually get either non-aligned or aligned fibers. So this is electrospinning. So you get very thin fibers, a few nanometer thickness is actually possible when you get these things. So this provides a very high surface to volume ratio, and it also provides a nanofibrous mat which resembles ECM in many of the tissues. So for these reasons, people actually work with such electrospun fibers. So right now people are also trying to use electrospun fibers on which you actually have these freeze dried material on top. So it will be more like a combination of both, which actually is more close to what an ECM would be. People are trying different things, and these are some of the technologies which are used for preparing the scaffolds. So we'll talk about 3D printing in the next class.